exponential functions pass the horizontal line test. I take any horizontal line I want, and it only crosses at once. That means this function is one-to-one and therefore has an inverse. The inverse of an exponential function is called a logarithm. These functions look to be in the form of this. F of x, the very simple ones look like this. Log base b of x. And just like exponential functions have many uses and applications, logarithms also have many uses and many applications. So if we have the original function here of the exponential b to the power of x, you see that b is the base. Well, b is also the base of the logarithm. X is the variable, and x is the variable on the inside of the logarithm. In fact, you can go back and forth. Let's say like a equals b to the power of x. I can change this to be log base b of a equals x. That's how you go from one side to the other side, is you take the logarithm or the exponent. So for instance, 2 cubed, this equals 8. Then I can rewrite this as 3 equals log base 2 of 8. It's the same thing but written in a different form. This one uses exponents, and this one uses logarithms. And all that I've done, all that really shifted here is this 2. If it's in the base on the exponential side, it's going to be in the base in the logarithm side. Now, what's important is that if you do take a logarithm, which removes this 2, this 3 is going to go down. It's not going to be in a power. It's going to be in the actual equation as a number, not a power. But the 8 kind of stays the same. The 8 just shifts over to be on the inside of the logarithm. In my mind, exponents are easier to understand, so sometimes it's better to change a logarithm back into an exponent if you're having trouble kind of understanding what it's saying. But both of them are useful, so it's good to get experience in both of them so that you understand them. Now, there are some specific things we need to be aware of for a logarithmic equation. Namely that b is greater than 0 and b does not equal 1. If b were equal to 1, you could think of this as something like this. Let's say f of x equals log base 1 of x. Let's actually use just specific numbers. Let's say a equals log base 1. I'm going to use different numbers than that. I'm going to use m equals log base 1 of n. What this means is the same thing as 1 to the power of m equals n. So I just took the logarithm and put it on this side as a power. That's all I've done here. But 1 to any power is 1. So this should equal 1 equals n. But what if I gave you the problem, for instance, 3 equals log base 1 of 2. Well, now I'm saying 1 to the power of 3 equals 2, which is not a true statement. You get a true statement is if this thing here is 1. And that's not telling us anything, really. It's not very useful. So we exclude that from a logarithm because this actually becomes a different type of function completely. So yeah, don't use 1 as a logarithm, but it also has to be greater than 0. You can't have negative bases. And I should also say that x must be greater than 0. So you can only have positive things on the inside of the logarithm. The reason why there's these stipulations of b greater than 0 and x greater than 0 and b not equal to 1 has to do with the resulting function that you have to graph. It's going to end up being this weird function that's kind of like a bunch of dots that are infinitely close but not actually connected. It's a math topic that's kind of a little bit more in depth for this discussion right now. Just suffice it to say, x must be greater than 0, b must be greater than 0, and b cannot equal -1 or just 1. Now let's look at the graphs of logarithms. So right here I've got 2 to the power of x, and note, I forgot to turn my mouse on. Note the asymptote here. It shoots off towards 0, and we'll also note this point right here, that 0 goes to 1. Now this is the exponential function. We're looking at logarithms though, so the logarithm is the inverse of an exponential. An exponential or a inverse function is flipped along y equals x. So if we take this function here and flip it along this y equals x line, we get the logarithm base 2 of x. You see how the asymptote, let me make it a little bit easier to see. The asymptote here going on this way is now flipped down to this side. This is the asymptote. And then, just like here, we have 0 equals 1. 1 goes to 0. It's the same point, just flipped along the y equals x line. And this goes on up to infinity. This goes on up to infinity. Now, a couple things. This asymptote is now at 0, meaning it never touches 0. It never crosses 0. It gets infinitely close to it, but never crosses it. You can keep zooming in, and you'll eventually find there's some gap between the y-axis there and the line. And this one shoots off towards infinity pretty quick. Not pretty quick. It does in fact go off to infinity, just like this one does in fact go off to infinity in its domain. This one will in fact go up and up and up continually, but it takes a very long time. It's a very, very slow rate of growth. All right, so that's what a logarithm is. It's really just this kind of a function here. Now let's look at some. This is this exact same function that I just had. Let's look at some transformations of a logarithm. So it's the same idea as always. A and B are both multipliers, so they're going to compress and stretch vertically and horizontally. C and D are just adders, so they're going to shift horizontally and vertically. So C, no surprise, it's just a shift left and right. D, shift up and down. Okay. B, let's start with A. When A is greater than 1, this is a stretch vertically. It's being stretched. So imagine putting your hand here, and you're pulling apart. It's getting stretched more and more and more and more. And then if it's less than 1, we have a compression vertically. It's getting compressed down to 0. What's interesting is that when we hit 0, well, we actually get completely compressed on right down to the x-axis. And the negative just flips it. And then less than -1 makes it stretch vertically again. Okay, let's look at b equal to, or changing b. When b is greater than 1, we have, it's hard to see. This is a little bit of a weird function, but this is actually a compression horizontally. You're taking your hand here and you're like shoving it closer to the to this y-axis here. It's being compressed. It's hard to see, especially, but you'll see at this point here. This point here is getting pushed inward. It's being compressed inward. See, when it was at 1, if I can get it there. Anyway, it's supposed to be right here. It's supposed to be at 0, 1, but it's being pushed inward and inward and inward. It's being compressed inward. Then if it's less than 1, it's actually being stretched. You see how this point right here is getting pulled away from 1, being pulled greater. And of course, if you get to negative, it's a flip, compression, and then a stretch. Or sorry, the other way around. It's a stretch and then a compression. Stretch is less than 1, compression is greater than 1. What I always like to look at is what happens when you go around 0. You see how it like gets stretched and then all of a sudden it's like not even there and then it flips on the other side. I always find that interesting. But that's transformations of logarithmic functions. So there are a few common logarithms, the most common being the natural log and base 10 log. In America, we use log base 10 of x. We say that this is just log of x. If there's no base written there, it is assumed to be base 10. And that's because our number system is base 10. It's directly related to that. So base 10 logarithm is a natural thing to use with our numbers. It works out very nicely in a lot of cases. Another base that we use a lot is base e. Just like I said in the previous video, the Euler's number is very, very useful. It's used in so many contexts, so many areas of mathematics, and so many applications, really. This is a special shorthand as this, ln. It's the natural log. That's what it's called, the natural log. It's not NL because logarithm starts with L, and that's what we're dealing with here is logarithms. But it's the logarithm natural. Think of it like that. Logarithm natural, ln. There is another one that's used, but you probably wouldn't see very often, is log base 2. This is really used for computations, since our computers are binary. So it's really base 2 system, and that is used as LG. But you probably never see this one. These are very common in mathematics, however. So there are a few basic properties that we'll talk about here. There's more in the next section, but for this section, there's just a couple. First off, log base b of 1 equals 0. This is because b to the power of 0 always equals 1. It's directly related to that rule of exponents. Log base b of b equals 1. That's because b to the power of 1 equals b. Same idea. Log base b of b to the x equals x. This is directly related to the fact that b to the power of x equals b to the power of x. If you just take a logarithm on both sides, that's what this statement is right here. What's important to note here is that a log base with the same base of an exponent, they cancel, and you're left with just the power. That's what's important to note here, that they're inverses, so they cancel. And just like this one, the flip side is b to the power of log base b of x. Once again, we have a base of an exponent of b and a logarithm base b. They cancel each other, and we get just x. So let's use these properties for a couple problems, and then we'll be done. Log base 2 of 16. What we're trying to do here is figure out, can we make the inside here be the same base as the logarithm? So log base 2 of 16, well, 16 is the same thing as 2 to the 4th power. 2 to the 4th power is 2 times 2 times 2 times 2, which is 16. And log base 2 and that 2 cancel, leaving us with just the power of 4. You can think of this in a different way. Log base 2 of 16 equals x. We're trying to figure out what is x equal. So let's rewrite this as an exponent. Right. It's going to be 2 to the power of x. This and this are equivalent statements. 2 to what power equals 16? Well, 2 to the 4th power equals 16. And that's really all we're doing here, but we're using properties of logarithms to calculate it. Now, let's look at one that's a little bit different. Log base, let me restart there. log base 3 of the square root of 27. I can rewrite this as log base 3, 27 to the 1/2 power. Square root is the same thing as 1/2 power. And 27 is 3 cubed. Now we just have a power to a power. Power to a power, we multiply them. So we have 3 times 1/2. 3 times 1/2 is 3/2. And the base of the logarithm and the base of the exponent cancel, giving us 3/2 being the final answer. Okay. Last one. Log base 5 of 1/25. All we're trying to do is get 5 to some power on the inside of the logarithm, because then we can cancel it. So 25 is 5 squared. We know that. So if we can get 1/25 to equal 5 to some power, then we're good to go. 1/25, that's the same thing as 25 to the -1. That's what the negative does, is it flips it. So if you want to undo a flip, just give it a -1 power. And we have 25 is 5 squared. Once again, we have a power to a power. So then we multiply the powers. 2 times -1 is -2. And now you see we can cancel those, giving us just the power -2. That's how you use the properties to calculate logarithms by hand. We also have a change of base formula to do a lot of this stuff, but calculators in general will be able to solve this as long as you make sure you're typing in the right base. Got to make sure you're typing in base 3, 5 in this case. A lot of scientific calculators that have where you can input the base, and so they can calculate it pretty easily.